So actually, it was years of pipe insulating experience that got me and my team interested in solving a pipe insulating problem. So with this, the interesting thing for me was that in the book, this equation number from chapter 10, 10.6-24, was one that would have been very helpful to me many years ago because it answers an important question about heat loss given whatever dimensions you have for insulation. So in solving for what our heat loss is from this equation, we can get Q equals K T0 minus T1. This is over R0 ln R1 over R0. So now all we need is to come up with what our variables are here, and we can start getting our values for Q0. So looking at the example of our pipe, first that we're given, with the given information, we may think that it's overspecified, but in actuality it's not. We're starting out with a 4-inch pipe, and in the first case we're starting out with 1.5 inches of insulation, which would then give us an R1 of 3.5 inches. Now, what may be challenging at this point is that when you get to be an engineer, you oftentimes look at problems as being much more complex than they're actually intended to be. So with this, we may think when it comes to finding the T average, we suddenly have to come up with, well, what is the volume? What is the temperature ratio as we go across here? And normally we would think, well, it's going to taper off very quickly, and then have to do all of this derivation. The thing is, this is an idealized situation, and if you actually look at the original PDF from which this is given, in the real world, this is not an ideal insulator. There is a seam running the entire length of it where it's going to be completely different than your idealized, and you're going to have a much higher amount of heat loss. As well, every 3 feet, you're going to have a butt joint, which with that, again, you have a great deal of heat loss. So with the information as it was given to us, what is the T average? Well, basically what we're starting with is T0 is actually an average because the running temperature of the line typically for a 700 degree mechanical hot water system, it's going to have 20 to 50 degree variance. So actually this is going to be running anywhere from, we'll say, 675 to 725. And actually for the outside temperature, if 100 degrees had been given to me, I would assume that they chose the coldest spot on the pipe because normally it would actually be, I would assume, more like 100 to 200 degrees. Okay, so given that we've been given this information, we really can't come up with any complicated profile for what the average per volume would be. So the best we can do is say, what is the average of T1 and T2? Well, it would be 700 plus 100 divided by 2, which gives us a 400 degree average. Which for this then we're calculating the K value, which conveniently we chose one that's right on the table, which is a K value of 0.45. And this is given in units of BTU, inch, over feet squared in degrees Fahrenheit. Okay, so plugging this into our equation, we now can solve for what that initial value was. And then plugging the numbers in, we get an equation that looks like this. 0.45, our T0, which was 700, minus 100, divided by our R0, which is 2 inches for a 4-inch diameter pipe, and then ln of our R1, which is the outside of 3.5 divided by 2. And this gives us a Q0 value of 241.24. And then canceling out our units, BTU, it cancels out inches underneath, so that gives us BTU feet squared per hour. And now, as specified in the problem, we want to get this down into what is the per foot loss of heat. So to do that, basically, what we're looking at for Q0 would be what our inner area, our inner circumference, basically, is what it calculates out to. Because this is in square feet, so to get this into linear feet, we simply need to multiply by whatever that circumference area is, so that then we simply have units of distance. So then for the 4 inches, for the circumference then becomes 4 inches times pi, which is 1.0472 feet. So to convert this down into what our heat loss per linear foot is, it's simply 241.24 BTU per feet squared per hour times our 1.472 feet. That gives us a linear foot loss of 252.6 BTU per hour per foot. Okay, so this gives us our first number that we need to compare. Now, switching this over for what the proposed would become, it simply matter now of changing our R1 becomes 4.5 feet. Now in this case, we're not given, and we really wouldn't know at this point, what our actual outside average temperature would be. Of course, theoretically it would be less, but we don't know how much less. So instead what we'll go ahead and do is we'll go ahead and keep the exact measurements that we have. So with our original equation, all we have to change is this 3.5 now becomes 4.5, in which case the Q0, this is now for 2.5 inches. This was at 1.5. This becomes, when we plug our numbers in, equals 166.475 BTU feet squared per hour, and then multiplying that again by the feet, which I forgot to put a 0 in here. This now becomes 174.33 BTU hour feet. So then in comparing these two, the current heat loss from the proposed heat loss, we now get a savings of 78.3 BTU hour feet. So this gives us the answer to our first part, and really it becomes a simple problem when you take out all of these assumptions, simply because what we're dealing with here is an evaluation problem. It's not idealized simply because we're dealing with a real world situation. As far as a lot of this information, basically the insulation companies have tried to dumb it down so we can do these calculations as quickly and as easily as possible. However, for me, it was simply not knowing that equation for a very long time, which held me back from being able to do a lot of these calculations. So instead, actually, for me, if the information that we gave you was from Johns Manville site. So instead, if you go to the Owens Corning, which was the one that I would have to use, their values are slightly different for their insulation, but they do come reasonably close because for them, when they specify 2.5 inches of insulation on a pipe running at 700 degrees, for 2.5 inches of insulation, they give a heat loss of 188. So that's within 10%. And also the differences they give, they have a different K value and they also have a different outside average temperature. So that is well within the reasonable range so that this gives us a good idea for cost estimates of whether it would be worth our break-even cost. And actually at this point, given what little I remember about the BTU cost and savings, this would approximately have a payback period of 2 years, which would make it a good decision to go forward with. Certainly another justification with this is if you go to the Owens Corning site, they don't even have specifications for 1.5 inches of insulation on a 700 degree line. So actually this is theoretical and is probably a much higher heat loss simply because they really haven't designed these numbers and equations to fit in to such a thin insulating category. Okay, so next we're asked to look at our return line, which in this case, we're told that it is returning at 300 degrees Fahrenheit. We'll go ahead and, for simplicity, assume that the jacket temperature also is 100 degrees, which now gives us an average temperature of 200. And then getting off the table, the information, we find a K value of 0.29. So now when we plug these numbers in and going back to our R1 of 1.5, this is now for our 300 degree return line. And also for clarity, when you have a mechanical system that's running out a supply of 4 inches, the return also has to be 4 inches unless otherwise specified. So that then is again, we're keeping our 2 inches here. So this time our Q0 is equal to, when we plug the numbers in, we get 51.82 for a linear heat loss of 54.26 BTU hour feet. And then changing out, we now take, if this were upgraded to 2.5 inches, we now get our Q0 is equal to 35.76 with now our heat loss is equal to 37.45. And in this case, the saving (16.8 BTU hour feet). Okay, so with our supply, we had a saving of 78 BTU hours per feet. And in this case, at 78, I estimated that it would be about 2-year payback period. There's no way you're going to get a decent payback period for only 16.8.